Alright, so let's take a look at section 7.1 and then 7.2. On these two sections, we're going to go over the differentiation and integration of the exponential function. So the exponential function we're going to focus on for these two sections will be natural base e to the x power, right? Okay. So in this particular section, we're going to go over properties of natural exponential function, and we'll learn how to differentiate natural exponential functions, and also we will learn how to integrate natural exponential functions. First of all, again, we're talking about f of x equal to e to the x power, right? E is a Euler number, Euler number, and e is approximately equal to 2.718. Okay. So the function f of x equal to ln of x, the inverse function of that, inverse function of the natural logarithm function is e to the x. Okay. If you look at a graph of these two functions, this is f of x equal to ln of x. The inverse function is e to the x, and these two, since they are inverse functions, so it's symmetrical with respect to y equal to x. Okay. Y equal to x is the symmetry line. Okay. In summary, right, the inverse function of the exponential function base e is natural logarithm function. Okay. So if you use a definition of the inverse function, f negative 1 of x. Okay. So in this case, f of x is ln of x. F inverse function is e to the x. So we're looking at function f of x, right? F inverse function is e to the x. So when you go back to function f of x, now replace x with e to the x, and you end up with ln of e to the x. They can put exponents in front, becomes ln of e. ln is log with base e, so it becomes 1. So it becomes x. Alright, so it basically verified their inverse function, right? Similarly, if you look at f negative 1 of f of x, that's going to be, for the inverse function, replace f of x, replace x with f of x, which is ln of x. So in this case, go back to inverse function e. Now change x to e to the x. If you simplify this, it becomes x as well. So again, by double checking these two properties, we know that we verify their inverse functions. So the inverse function of natural logarithm function f of x equal to ln of x is called the natural exponential function, and it's denoted by inverse function of f of x equal to e to the x. Then you can replace the inverse notation with y, so y equal to e to the x. And if you take ln on both sides of the equation, right hand side remains ln of y, left hand side cancel that, x goes in front, becomes x. In this case, x equal to ln of y. So y equal to e to the x if only if x is equal to ln of y. Okay, and following just two inverse relationship between the natural logarithm function and exponential function with base e. Okay, so ln of e to the x equal to x, e raised to ln of x power equal to x. So this is summary of the inverse relationship. Now let's take a look at this exponential equation. I'll try to solve it. Solve for x. So first of all, anytime when you have an exponential equation, you take ln from both sides of the equation. And the exponents on the right hand side of the equation, exponents goes in front, it becomes ln of e. And ln of e becomes 1. X plus 1 times 1 ln of 7. Now simplify the equation, you get x plus 1 equal to ln of 7. Then isolate x, subtracting 1 from both sides of the equation. So x equal to ln of 7 minus 1. And in the background, it's a solution solve for x. Okay. Let's review a couple properties of exponential functions. That a and b be any real number. So you multiply two exponents with the same base e. Then you add in the exponents. So the result becomes e to the a plus b. Okay. You divide two exponents base e to the a divided by e to the b. You keep the base e and subtract the exponents using a minus b. Okay. Just a couple properties, we use a lot in pre-calculus. The inverse function shares many properties with original function. So as you can see, this is a graph of the y equal to e to the x. So the way you come up with the graph, you just need 5 order pairs, right? In the middle, you're gonna set x equals 0. So y equal to e to the 0, e to the 0 becomes 1. So all the exponential function has a y-intercept, which is 0, 1, right? This is the y-intercept. And you can pick a couple numbers on the left hand side of 0. So we pick x equal to -2 and -1. On the right hand side of the 0, you pick 1 and 2. So for y value, when x equal to -2 is e to -2. So that becomes 1 over e squared. That 1 over e squared is approximately 1 over 2.71 a squared. That's 0.1 something, right? So it's 1 over e squared. And that's this order pair, okay? Second order pair, y equal to e to -1. When x equal to -1, it becomes 1 over e to the 1. It's 1 over e. 1 over e, that's 0.3 something. So that's second order pair, -1, 1 over e. Third order pair is y-intercept 0, 1. The fourth order pair, when x equal to 1, y equal to e to the first power, which is e. So this is e. So the fourth order pair is 1, e. If you want another order pair, we'll be setting x equal to 2, so e to the second power. So that's 2.718, approximately equal to 2.718 squared. So that's somewhere is 8 point something, right? So once you have all these order pair connected, you get a graph of the function y equal to e to the x. And as you can see from left to right, if you're going from left to right, the graph is increasing, right? It's going upward. and then in terms of concavity, it's concaving upward, right? Concaving upward. So two important property about exponential function with base e: it's increasing and concaving down upward. So let's take a look at some properties of the natural exponential function. First of all, the domain, it's all real numbers, and the range, if you go back really quick, domain is all real numbers from negative infinity to positive infinity. The range, all the y values is above x-axis, so the range is from 0 to positive infinity. I take a domain range. The function f of x equal to e to the x is continuous. If you go back, you don't see no code, no gap, no jump, no breaks. That indicates continuous. It's increasing, and it's one-to-one relationship, right? If you perform a horizontal line test, you only have one intercept. That means it has a unique inverse function. Just one unique inverse function. If you perform a vertical line test, again, you're gonna only end up with one intercept. That means it's one-to-one relationship, so it's a function. Okay. So it's one-to-one on its entire domain. The graph of f of x equal to e to the x is concaving upward on its entire domain. Concave upward. The limit when x approaches negative infinity for e to the x is 0. I'm going to show you how they derive that. X approaches negative infinity, e to the x becomes limit when x approaches negative infinity, e to negative infinity, and this becomes 1 over e to infinity, basically, right? So limit e to the infinity is infinity. Okay, so it's 1 over infinity, that gives you 0, right? Any constant divided by infinity is 0. For limit, second limit when x approaches infinity for e to the x is infinity, so limit x approaches infinity, e to the x. Replace x with infinity, you get limit x approaches infinity, e to infinity power becomes infinity. The limit of the infinity is infinity, right? That's why limit when x approaches infinity, positive infinity for e to the x is also positive infinity. And next thing, let's take a look at derivative of the exponential function. Okay, the derivative of exponential function base e is itself. So the most useful characteristics of natural exponential function is that derivative is itself, right? And putting another way is y prime equal to derivative of y equal to itself equal to y. So and this is also a differential equation. So the differential equation of y prime equal to y, we know that y equal to e to the x. And this is simplest differential equation you can ever have. So let's take a look at the theorem about the derivatives of the natural exponential function. So derivative of e to the x is equal to the x. So derivative of natural exponential function is itself. and derivative of e to the u, and u is any other expression besides x, right? So it becomes eu du of dx is eu times u prime, right? Okay, that's what it means. All right, so let's take a look at how we find the derivative of e to the 2x minus 1. So if you look at the exponents is not x, so we're setting that equal to u equal 2x minus 1. So the u prime derivative of 2x is 2, derivative of -1 is 0, so it becomes 2. So derivative of 2x minus 1 is 2. Okay, so apply the property from the previous PPT. The derivative of this is eu times u prime. So eu is e to the 2x minus 1 times u prime, which is 2. So the answer is 2 times e to 2x minus 1. Okay. It's a very straightforward process of finding the derivative of the natural exponential function. In the second example, we have a derivative of e to -3 over x power. So in this case, u equal to -3 over x. Okay, and you can rewrite this as -3 times x to -1 power. If you want to apply the power rule here, right? So u prime is equal to -3 times -1 times x -1 minus 1. -3 times -1 becomes 3. 3 times x to -2 power. You rewrite it, becomes 3 over x squared. Okay. So now derivative of e to the power of -3 over x becomes u prime. Okay. eu is -3 over x, right? u prime 3 over x squared. So the answer is 3 over x squared times e to the 3 over x power. You can make a fraction and flip to the denominator, and it becomes positive exponents. Okay, in the background is a detailed solution. We can also go over that. And derivative is fairly simple, and let's take a look at the integrals of the exponential function. Integral is also what we call integration. The process of finding integral is called integration. The integral is also called antiderivatives, meaning it's the inverse process of derivative. So that's why it's called antiderivatives. So let's take a look at integrals of an exponential function. So integral of since that the integral is inverse process of derivative, so meaning we're given the derivative e to the x, like going backwards to find the original function. So integration of e to the x is ex plus c, right? Plus constant, because derivative of constant is going to be 0. So that's why when you're going backwards, you always add a constant c, because derivative of ex plus 1, that's ex, right? Derivative of ex is ex, derivative of 1 becomes 0. Derivative of any other number minus 1, ex minus 1, derivative of ex is ex, derivative of -1 becomes 0. So as you can see, you need to add a constant, because c could be any number, right? Okay. And integral of EU du equals to EU plus C. Similarly, alright, so let's take a look at this example, and let's find the integral of e to the 3x plus 1 power dx. In this case, u is not x, so that means we gotta set u equals 3x plus 1, and then du over dx equal to, we differentiate u with respect to x, so derivative of 3x is 3, derivative of 1 is 0, so it's 3 plus 0, which is 3. So du over dx equals 3. If we turn into a proportion 3 over 1 cross multiplying, we end up with 3 dx equals du. So dx, divide 3 from both sides of the equation, dx becomes du over 3. Okay, so keep that in mind. So now that's just simplified. We write this integral with respect to u. So 3x plus 1, that's u, so eu dx equal du over 3. So you can just put the fraction in front, and that becomes 1/3, then u du, right? So it's going to be 1/3 u du is eu plus c. Okay, so it becomes 1/3 of u. 1/3 of c, we can just use another constant to replace it, so it's plus c. Okay, you know what, let me just keep it simple without putting the parentheses. So get rid of parentheses. It probably look a little bit easier. One-third of u plus c. Okay. Now very last step, replace u with 3x plus 1. So you find the antiderivative of e to the 3x plus 1. E to the 3x plus 1 c. Okay, so you find the integral of e to the 3x plus 1 with respect to x. Okay, so you can call this u substitution. This method works very well in terms of finding the integral of the natural exponential function. That's pretty much it for this section. Background is detailed solutions. So